Infant stars that have blasted away surrounding gases and only just begun to shine have also been found. How does the Hubble Space Telescope communicate the digital images it takes in space back to Earth? With the Wide Field Planetary Camera 2, each image is composed of a square grid with 800 picture elements, or pixels, on each side, for a total of 640,000 pixels. Each pixel registers light intensity, or brightness. Brightness is classified into, for example, 10 levels, and each pixel assigned a shade from 0 to 9, so converting the signal into numerical data. The darkest pixels are given a value of 0, the brightest a value of 9. An image will then consist of a string of numbers, in this case beginning 342301, reading from left to right in the top row. This series of numbers is radioed to Earth. The numbers are then converted back to light intensities according to the same rules. Called telephotography, this method allows numerical values to be transmitted to reconstruct the original image. If the image is photographed separately through 3 different filters, say red, blue, and green, we can produce a composite full-color picture by superimposition. But there is an obstacle to radio transmission. The Earth station cannot receive transmissions when the space telescope is at the far side of the Earth. To get around this problem, a digital communications system called TDRSS, for Tracking and Data Relay Satellite System, is used. There are 3 satellites like this one, each equipped with 2 4.9-meter dish antennas in geostationary orbit at an altitude of 36,000 kilometers. They allow digital data from the space telescope, wherever it may be, to be transmitted back to the Earth station at a rate of 1 million bits per second. It is only because of this digital observation system that scientists on Earth can obtain such detailed images of celestial bodies. This is the Cat's Eye Nebula, as photographed by the Hubble Space Telescope. A central whitish star shows up distinctly in a red cloud of gas expanding out into space. A detailed computer analysis of this image showed that the nebula was actually composed of 2 cocoon-shaped gas clouds, one large and one small. The structure of the nebula, as determined through observation, can be described using computer graphics in the form of a 3-dimensional image. Astronomers speculate that the larger of the 2 clouds was ejected from the central star at an earlier stage, while the smaller one was formed more recently. This is the star Eta Carinae in the constellation Carina, visible in the Earth's southern hemisphere. It appears at the heart of a nebula that looks like 2 huge mushroom-shaped clouds joined together. The star, which is more than 100 times as massive as our Sun, is coming toward the end of its life. The surrounding gas, glowing red, is expanding at a fantastic speed of 1,400 kilometers per second. Astronomers predict that Eta Carinae will die in the near future in a spectacular explosion. The instant a star undergoes such a giant explosion has actually been observed. This is supernova 1987A, the remnant of a star in the Large Magellanic Galaxy. The blast of the explosion is carrying material through interstellar space at tremendous speeds. The gases ejected from the star describe 3 mysterious rings. Analysis has shown that these 3 rings are independent of one another. How they formed, however, remains a mystery. Equipped with digital observation instruments, the Hubble Space Telescope continues to photograph the mysteries and wonders of the cosmos, and to communicate them to Earth in the form of digital data.
With the computer as its tool, humankind has made it possible to handle observation data at will and create within the computer a picture of the universe that otherwise would be impossible to visualize. Now let's use the powers of the computer to witness an astonishing fact.
The boundless universe and the eternal flow of time. We tend to think of the universe as being eternally unchanging, no matter how far we go in space and in time. But the universe is not static. It changes with every moment. Orion might be considered the most beautiful of all constellations in the celestial sphere. The red star shining at the top left is Betelgeuse. It is 1,000 times the size of our Sun. It is an old star that is coming to the end of its life. The first magnitude star at the bottom right is Rigel. It shines with a bluish-white light. It is a very youthful star. The stars that make up Orion do not actually belong together as a group located in the same region of the cosmos. Let's feed the accurate distance of each star in Orion from Earth into a computer and take a sideways look at the relative positions of the stars within the constellation. Betelgeuse is 500 light-years from Earth. The bluish-white Rigel is at a distance of 700 light-years. But the 3 stars in the belt of Orion lie much further, being between 1,300 to 1,500 light-years away. The shape of any constellation in the night sky only tells us the apparent positions of the member stars, a 2-dimensional projection as viewed from Earth. Now, let's use the computer to go back in time and see how Orion appeared from Earth 1,000,000 years ago. Pay close attention to the motion of the red star, Betelgeuse. Orion looked quite different a million years ago from what it does today. Now, let's do some calculations to see what Orion will look like a million years from today. The stars passing rapidly in the foreground are coming in from outside the constellation. All the stars in the night sky, and not just those in Orion, are traveling at different speeds on their separate ways. The shapes that our familiar constellations take, therefore, change with time. In a human lifespan, not much more than 80 years, stars don't appear to move at all. But we know that each star is actually in continuous motion at speeds more than several hundred kilometers an hour. Nothing in the universe remains still. Everything is continuously undergoing violent changes, even as we watch it.
By feeding observation data into a computer and performing calculations, humankind can now transcend time and visualize the universe as it was in the past and as it will be in the future. Today, the computer plays a central role in observations made with giant ground telescopes as well. Now let's take a look at some of the results obtained in digital ground-based astronomy.
This view is from the summit of Mauna Kea, 4,200 meters above sea level on the island of Hawaii. This spot is one of the best on Earth for making astronomical observations. Dr. David Jewett of the University of Hawaii has been searching for a yet undiscovered planet thought to lie beyond Pluto